Hi everyone. Today I'll be talking about atomic X-ray spectrometry. X-ray spectrometry, like optical spectrometry, is based on measurement of emission, absorption, scattering, fluorescence, and diffraction of electromagnetic radiation, but in the X-ray region, which is a shorter wavelength or much higher energy radiation than we've been looking at so far with infrared, visible, and UV. So now we're looking at the X-ray region, which corresponds to 10 to the minus 10 meters in terms of wavelength. X-rays are produced by deceleration of high-energy electrons or by electronic transitions of electrons within the inner orbitals of atoms. For analytical purposes, X-rays are generated in four ways. The first is bombardment of a metal target with a beam of high-energy electrons. The second is exposure of a substance to a primary beam of X-rays to generate a secondary beam of X-ray fluorescence. Thirdly, a radioactive source whose decay emits X-rays. And finally, synchrotron sources. We are going to focus on two types, so bombardment of a metal target and radioactive decay. So the first kind of source we're going to talk about is the X-ray tube. It's the most common source of X-rays, where electrons from a heated tungsten cathode, as you can see here, are accelerated towards a copper anode by approximately 100 kilovolts. Now, the copper anode, as you can see here, has a target metal embedded in it. This can be either tungsten, chromium, copper, molybdenum, and cobalt are the common ones. So the electrons collide with the target atoms, and deceleration gives off X-ray photons, producing continuous radiation, or sometimes known as broadband radiation. And this particular type of X-ray broadband radiation is known as Bremsstrahlung, as you can see here with this tungsten target. And the accelerating voltage is what's determining the wavelength. So you can see here for the different curves, these are the different accelerating voltages, and they're producing a slightly different range of wavelengths. Now, under some conditions, a line spectrum is superimposed on the continuum, as you can see here in the case of a molybdenum target. For both spectra, however, the short wavelength limit, or lambda naught, is depending on the accelerating voltage. So how do we get line spectra from these electron beam sources? Well, when electrons bombard the target elements, their core electrons are ejected, and other electrons fall down from higher energies to fill these core vacancies. And there are two series of emission lines. The first is the shorter wavelength group, known as the K series. And this is when the first principal quantum level, or n equal to 1, as you can see here, is being filled from higher energy levels. So it doesn't matter which higher energy level the electron is coming from, but it's filling these n equals 1 level. Now, the second series is known as the L series, and this is a longer wavelength series, where the n equals 2 principal quantum number, the second principal quantum number, is being filled from higher energy levels. So, and these are designated depending on where the electron is coming from as either alpha, beta, or gamma. And so for the example of this molybdenum target, you can see that we are looking at the K beta and K alpha emission lines. The second kind of source are radioactive sources. So radioactive decay results in excited nuclear states, and then decay to the ground state is what's producing X-ray and gamma rays. And this is again through continuum X radiation. So for example, we'll take iron 55. What can happen is the iron 55 decays into manganese 55. And this produces a frequency, or a wavelength, corresponding, so for in the case of manganese, to the K alpha line at 2.1 angstroms. And you can see in this table here that there are other examples of elements that radioactively decay, giving off X-rays. So next up we have wavelength selection. And wavelength selection is performed by a diffracting crystal, which is mounted on a goniometer. So this crystal mount here is called a goniometer, and this is just used for precise control of the angle. So you can control the angle of the crystal very, very precisely. Scattering of X-rays from a crystal lattice results in constructive and destructive interference, and this is because the lattice spacing, d, as you can see here, is on the same order as the wavelength of X radiation, resulting in diffraction. So if we take a look at this figure, here radiation strikes a crystal surface at an angle theta, as defined here. And just to note that this is a sort of odd definition of theta with respect to the surface rather than with respect to the normal, as we've seen up until this point. And this is just something special to the X-ray community. They decided to define it this way instead of with respect to the normal. So scattering occurs as a result of interaction with atoms and this incoming radiation located at O, P, and R. So if the distance AP and PC equal m lambda, and again I'm using m here instead of n as in the textbook where m is just an integer, the scattered radiation will be in phase at O, C, and D. And the crystal will then reflect X radiation. But ray 2, so if we're looking at the second ray here, travels further than ray 1 by a distance of d sine theta. So by the time both beams are reflected, since this distance is the same, also d sine theta, so by the time both beams are reflected, ray 2 must travel an extra 2d sine theta in order to be in phase with ray 1, which is traveling a shorter distance. And so from this we end up with Bragg's law. So this is Bragg's law, or Bragg's equation, where m is the diffracted order, which is again just an integer. And as a result, X-rays are only reflected from the crystal if sine theta is equal to n lambda over 2d. Oh, sorry, I'm getting confused with the textbook. M lambda over 2d. At all other angles, destructive interference occurs, and you do not get that wavelength to be reflected. But in order to cover a useful analytical range of X-ray wavelengths, you're going to need a few different crystals available with different lattice spacings in order to be able to pick and choose those different wavelengths. So next up we have detectors. And in contrast to those we've seen so far, X-ray detectors are operated as photon counters, in that they record the number of counts per unit of time. And the most common are gas-filled transducers. So that's the one we're going to focus on here. So when X-rays travel through an inert gas, either argon, xenon, or krypton, ionization of the gas occurs, producing both ions and electrons for each X-ray quantum or X-ray photon. This results in enhanced conductivity of the gas, and the photoelectrons that are produced from this ionization, in this case argon, these ions ionize several hundred other argon atoms. And so when you apply a voltage to this whole setup, the electrons migrate towards this wire anode here, and the resulting current is then measured. So what we get out of all of this, hopefully, is an X-ray absorption spectrum. And these contain a few well-defined peaks, as you can see in the figure here. The wavelengths of the absorption maxima are characteristic of the element and are largely independent of its chemical state. Absorption of an X-ray photon causes ejection of a core electron, resulting in an excited ion. Now, the energy of the incident radiation goes into two things: the kinetic energy of the photoelectron, as well as the potential energy of the excited ion. The highest probability for absorption occurs when the photon energy is equal to the energy required to remove a K-level electron, so the closest to the atom, to the nucleus, and in other words, the kinetic energy of the photoelectron approaches zero. So for lead, which you can see in this figure is the blue spectrum, the first absorption peak occurs at about 0.14 angstroms. And this corresponds to the energy required to eject the highest energy K electron. But at wavelengths just larger or longer, the incoming radiation is not great enough to remove a K electron. And so you see this abrupt decrease in the absorption. And this is known as the absorption edge. But at wavelengths shorter than 0.14 angstroms, the probability of ionization gradually diminishes, resulting in this sort of smooth decrease in the absorption. Now you can see that there's also additional peaks at longer wavelengths, and these correspond to removal of L-level electrons. That's why they're labeled as the L edges. And this figure, as you can see in black, also shows the X-ray absorption spectrum for silver. And the longer wavelength of this absorption maximum for the K edge, as you can see here, reflects its lower atomic number than that of lead. And I'm going to leave you to ponder why that might be.